Hello friends, I welcome you to my lecture on variational problems with moving boundaries. So far we have considered variational problems where the boundary points x1, y1 and x2, y2 are fixed, and we want to extremize the functional integral x1, y1 to x2, y2 fx by y dash dx that we had considered initially. Now we will be considering the case where either both the boundary points x1 y1 x2 y2 are fixed are moving, or one of them is moving. So let us take for example, suppose we want to find the shortest distance between a point x1 y1 on a curve y equal to gx and a point x2 y2 on another curve y equal to hx. Then we would like to find the extremum value of the functional I by x equal to integral x1 to x2 fx by y dash dx, where fx by y dash is the distance between the distance ds. This is ds, so that is under root 1 plus dy by dx whole square into dx. So this fx by y dash dx becomes under root 1 plus y dash square dx, and the points x1 y1 and x2 y2, either both of them are moving, or one is fixed, the other one is moving. So let us take a first problem where we will see that both the boundary points x1 y1 and x2 y2 are moving. So and at the free boundaries x1 y1 x2 y2, we know that we have the transversality conditions fx by y dash plus g dash minus y dash into partial derivative of f with respect to y dash at x equal to x1 is 0. This is for the curve y equal to gx, and for the curve y equal to hx, similarly we have the other transversality condition fx by y dash plus h dash minus y dash into delta f by delta y dash at x equal to x2 equal to 0, where x2 y2 lies on the curve y equal to hx. So the problem is therefore to find the shortest distance between the points x1 y1 lying on the curve y equal to gx and x2 y2 lying on the curve y equal to hx. For example, suppose we have one curve y equal to gx as y equal to x square, and the other curve y equal to hx as the straight line x minus y equal to 5. So let us see, we can draw them. So this is y equal to x square, y equal to x square, and x minus y equal to 5. So when you put y equal to 0, we get x equal to 5, and when we put x equal to 0, we get y equal to minus 5. So the straight line passes through 0 minus 5 here and 5 0 here. So let us take one point x1 y1 here and another point x2 y2 here, and we want to find the shortest distance between the curve y equal to x square and y equal to x minus y equal to 5. Now you have seen that I have drawn the line joining x1 y1 to x2 y2. We can see that the shortest distance will, I mean the extremal of this problem under root 1 plus y dash square actually is the shortest is the line. Say if you have here fx by y dash, the extremal of this will be a straight line. This is equal to under root 1 plus y dash square. So if you differentiate, so the Euler's equation here is partial derivative of f with respect to y minus d over dx, partial derivative of f with respect to y dash, and what we get here is since f depends only on y dash, so we have the partial derivative of f with respect to y 0 minus d over dx of partial derivative of f with respect to y dash. So that means 1 upon 2 under root 1 plus y dash square into 2y dash equal to 0. So we will get y dash upon under root 1 plus y dash square equal to some constant c when we integrate both sides. So r we can say by this implies by dash square equal to c square 1 plus by dash square 1b square both sides. So, what we get is by dash square into 1 minus c square equal to c square, or we can say dy by dx is equal to under root c square upon 1 minus c square, which we can write as some constant c1. So, by gives you c1x plus c2 when we integrate. So, extremal of the functional integral x1 to x2 under root 1 plus by dash square dx is actually the straight line. So, we have, but these points are moving x1 y1 x2 y2. So, let us see the extremal for this problem, but the extremal will be a straight line. Let us see what is that straight line. So, we start with the transversality condition. The transversality condition here is what for the function for the curve y equal to gx. Y equal to gx is x square. So, the transversality condition for the curve y equal to gx will be partial derivative of f with respect to y dash. No, this is f by y, f x by y dash. So, f x by y dash plus the g dash derivative of g with respect to x minus y dash and partial derivative of f with respect to y dash at x equal to x1 equal to 0. This is the transversality condition for the curve y equal to gx on which x1 y1 lies. So, here f x by y dash is given to be 1 plus y dash square to the power half, and this is f x by y dash. This is derivative of gx with respect to x, that is g dash 2x minus y dash, and then this is partial derivative of f with respect to y dash. So, y dash upon under root 1 plus y dash square at x equal to x1 equal to 0, and similarly the transversality condition for the other curve y equal to hx. So, this is I can write y equal to x minus 5. So, the other curve is y equal to hx, where hx is x minus 5. So, we have again f x by y dash as 1 plus y dash square to the power half, g dash will be replaced by h dash, and h dash is equal to 1. So, the other transversality condition is f x by y dash plus h dash minus y dash into partial derivative of f with respect to y dash at x equal to x2 equal to 0 gives you this equation 1 plus y dash square to the power half, h dash x is equal to 1 minus y dash upon under root 1 plus y dash square to the power half is equal to 0. These are two transversality condition. The general solution of the Euler's equation for the functional 3, that is this, for the function, this is the general solution for this is this one, y equal to c1x plus c2x, the straight line, y equal to c1x plus c2, where c1 c2 are arbitrary constants. Now, from here we can see that y dash is equal to c1. So, y dash is equal to c1. If you put y dash equal to c1 in equation 4, what we get is here if you put y dash equal to c1, what we will get? One plus c1 square to the power half plus 2x minus c1, y dash is c1, or c1 upon 1 plus c1 square root equal to 0. So, what we will get is and x is equal to x1. So we can multiply by under root 1 plus c1 square. So we get 1 plus c1 square 2c1 x1 minus c1 square equal to 0. So this cancels and we get 1 plus 2c1 x1 equal to 0. And from the equation 5, let us see the equation 5. From the equation 5 we have 1 plus y dash square. So 1 plus c1 square raised to the power half, and then we get 1 minus y dash. So 1 minus c1, and then we get c1 upon under root 1 minus 1 plus c1 square equal to 0. So what we will get? 1 plus c1 square. When we take the LCM, we get 1 plus c1 minus c1 square equal to 0. So we get c1 equal to minus 1 from the transversality condition 5. Now so c1 equal to minus 1, and thus x1, if you put c1 equal to minus 1 here, you get x1 equal to half. So thus c1 equal to minus 1 and x1 equal to half. Now let us go to so since both the endpoints x1 by 1 x2 by 2 lie on the extremal y equal to c1x plus c2, they will satisfy this equation. So we get c1x1 plus c2 equal to y1, and y1 is equal to x1 whole square, and then we get c1x2 plus c2 equal to y2, and y2 is x2 minus 5. Now let us use c1 equal to minus 1 here and x1 equal to half here. So then you can easily see that c2 comes out to be 3 by 4 and x2 comes out to be 23 by 8, and thus the required extremal line is y equal to c1x plus c2. So c1 was minus 1 and c2 is 3 by 4. So we get y equal to minus x plus 3 by 4, and the shortest distance between the given parabola and the straight line is integral x1 to x2. x1 is half, x2 is 23 by 8 under root 1 plus y dash square dx, where y dash is c1. So 1 by 2 integral 1 by 2 to 23 by 8 under root 1 plus c1 square dx, but c1 is equal to minus 1. So we will be getting 1 plus 1, that is square root 2. So square root 2 into 23 by 8 minus half, that is 19 root 2 by 8. So this is how we can get the shortest distance between the given parabola and the straight line. We can, instead of this, we can also use the formula under root x1 minus x2 whole square, st equal to because we know x1 by 1 as well as x2 by 2, and we get 19 by root 2 by 8. Now so here we took a problem where both the points x1 by 1 and x2 by 2 were moving. Now let us take a problem where one of the end points is fixed, x1 by 1 say for example is 1 0 and x2 by 2 lies on the ellipse, and we want to find the shortest distance between the point A, that is 1 0, and the ellipse 4x square plus 9y square equal to 36. So let us draw this draw the curves and the plot the point. So if you, so we have the ellipse 4x square plus 9y square equal to 36. You can see here that when y equal to 0, x is equal to plus minus 3, and when x equal to 0, y equal to plus minus 2. So we can draw the parabola, sorry, ellipse. So this is 3 0 minus 3 0 here is 0 minus 2, here is 2 0, and 1 0 point, let us say this is 1 0 point. So we have to find the shortest distance between the point 1 0 and the ellipse. Now you can see that ellipse is symmetric with respect to x as well as y axis. So if this is your point x1 by 1, this is your point x2 by 2, then you can see that if the straight line, and again we have that the extremal or the solution of the extremal the functional I by x equal to x1 to x2, as we have seen in the previous problem, under root by 1 by plus 1 plus by dash square dx lies along the is the straight line. So by equal to c1x plus c2. This is the solution of the given functional. So if this point is x2 by 2, then you can get the corresponding bisymmetry the other point also. There actually, so there will be two points x2 y2 and it's this point. This also will have the same distance from 1 0. So what we will be doing is that when we solve this equation for the value of y, we shall consider y to be positive. To get, so by symmetry we can get the other point also. Now this is the equation 4x square plus 9y square equal to 36 and x1 equal to 1. This is x1 equal to 1. Now what we do is we can solve the equation y equal to this equation. Let us say 4x square plus 9y square equal to 36 can be written as y equal to 2 by 3 under root 9 minus x square. So while solving this equation, as you can see, we have taken the positive value of the square root. So we are taking this the point x2 by 2 here. You can, if you take negative value, you get the point which is symmetric with respect to x axis. Now extremal of the given functional is a straight line. So by equal to c1x plus c2, x1 by 1 lies x1 by 1 is 1 0, which lies on this line. So we get c2 equal to minus c1, or x2 by 2 also lies, x2 by 2 is a point on the curve, x2 by 2 lies on the line by equal to c1x plus c2. So by 2 equal to c1 x2 plus c2, and when we put c1 equal to c2 equal to minus c1, we get here c1 times x2 minus 1. So by 2 is equal to c1 times x2 minus 1. So this is the value of by 2, and we also have c2 equal to minus c1. Now we go to the transversality condition. Before that, x2 y2 point lies on the parabola. So 4x2 square plus 9y2 square is equal to 36. So putting the value of by 2 equal to c1 times x2 minus 1, we get this equation 4x2 square plus 9c1 square x2 minus 1 whole square equal to 36. Now let us write the transversality condition at the moving point. x2 by 2 is a moving point. So at x2 by 2 which is f plus g dash minus y dash into the partial derivative of f with respect to y dash. So here fx by y dash is under root 1 plus y dash square. So we have 1 plus y dash square raised to the power half, and gx is equal to, this is gx 2 by 3 under root 2 9 minus x square. When we differentiate g with respect to x, we get minus 2x upon 3 under root 9 minus x square minus y dash, and the partial derivative of this fx by y dash with respect to y dash is y dash over under root 1 plus y dash square at x equal to x2 is 0. This is the transversality condition at the moving point. Now we have y dash equal to from this equation y equal to c1x plus c2, y dash equal to c1. So let us put that in the transversality condition. We will get 1 plus c1 square to the power half, and here we will get minus 2x2 upon 3 under root 9 minus x2 square minus this by dash which is c1, this is c1 upon 1 plus c1 square under root. So we get this equation. So this equation we get. This is what we get from the transversality condition. Now when you simplify this equation, after simplification what you will get is 3 under root 9 minus x2 square equal to 2c1 x2. Now what we have, by 2 equal to c1 into x2 minus 1. So let us replace by 2 equal to 2 by 3 under root 9 minus x2 here. Then this is equal to c1 x2 minus 1, or we can say 9 minus x2 square equal to 3 by 2, into C1 x2 minus 1. So, this equation and this equation be now combined together and arrive at this equation 2 by 3 C1 x2 equal to 3 by 2 C1 into x2 minus 1. Now, there arise two possibilities. One is that C1 is equal to 0. When C1 is equal to 0, what will happen? Then C2 is also equal to 0. So, what will happen? By equal to 0 we will get. By equal to 0 means x axis. Now, x axis means the distance from 1 0 to the ellipse will be along the line this. That means this distance from 1 0 to 3 0, and the distance will be SD will be equal to 2 here. So, if here the distance is 2, if you take C1 equal to 0, but if you take C1 non-zero, then what we will get? From this equation we will get x2 equal to 9 by 5, and from the relation by 2 equal to 2 by 3 under root 9 minus x2 square by 2 comes out to be 8 by 5. So, we get x2 equal to 9 by 5. So, this is 9 by 5 8 by 5, and so the distance of 9 by 5 8 by 5 from 1 0 is 4 by root 5. So, this distance is 4 by root 5, and similarly by symmetry the other point here is 9 by 5 minus 8 by 5. So, this. Now, you can see that 4 by root 5 is less than 2. 2 we got when we took C1 equal to 0, and when we took C1 equal to 0 we got the line by equal to C1 x plus C2 x s by equal to 0, which is the x axis, and so the shortest distance from 1 0 to the ellipse was the distance between 1 0 and 3 0 point, which is 2. And when C1 is not equal to 0, we have got SD equal to 4 by root 5, and clearly 4 by root 5 is less than 2. So, this SD is achieved along the line by equal to 2 times x minus 1. So, here actually when you calculate C1 then it will come out to be 2. You can see from here by 2 equal to 8 by 5, by 2 equal to 8 by 5, C1 times 9 by 5 minus 1. So, this will give you 8 by 5 equal to C1 times 4 by 5. So, this gives C1 equal to 2, and C2 is equal to minus C1. So, it is minus 2. So, by is equal to C1x plus C2, that is by equal to 2x minus 2 or 2 times x minus 1. So, the shortest distance is achieved along the line by equal to 2 times x minus 1, and thus we can say that the extremal curve is by equal to 2 times x minus 1, and the shortest distance is 4 by root 5. With this I would like to conclude my lecture. Thank you very much for your attention.